introducing the next speaker. This is a postdoctoral fellow that I met prior to coming to the University of Washington when I was a master's student at the Fifth Vanderbilt Bridge program. I am very happy to introduce Dr. Richard Galvez, a Moore Sloan Data Science Fellow at the New York University and a dear friend.
Give me one minute.
Hi everybody. So, in light of a more sort of relaxed, laid-back sort of theater-driven experience on astronomy, I decided to just go with a really random question that kind of was asked me about a week ago. And it's usually, so whenever I go home for the holidays, my little nephew, he usually asks me a bunch of random science questions. Whatever occurs to him in his mind. So, some are really basic, right? Like, why is the sky blue? Stuff like that. And, you know, basic questions. And, you know, I'm just like, well, I'm a damn astrophysicist. I know the answer to this. I know why this guy's blue. But, you know, when he started getting a little bit older, he started asking some things which were maybe a bit more advanced. Like, for instance, he asked me one time, like, hey, how do you think, how fast do you think Santa Claus has to travel, like during Christmas to deliver all the presents to all the kids? So we sat down and we calculated it. Surprisingly, under very conservative estimates and assumptions, the speed is pretty close to the speed of light. And actually I was like, hey Ethan, so do you think that's kind of fishy or hint, hint, you know? He's 9, whatever. He was 9 then. And he's like, yeah, that's kind of fast, isn't it? It's hard, right? Or, like, yeah, it's a lot of energy, you know. And after that, he was like, hey, how many chocolate chips do you think exist on planet Earth? Do you think like all the kids can actually make all the cookies for like Santa? So we sat down and calculated it. It turns out it's about like we're quite short. It's quite hard. In fact, the bottleneck is like how quickly one can purchase chocolate chips at the grocery. Anyway, it's complicated, but we're at like a 70% shortage of chocolate chips. So then I was like, hey Ethan, isn't that fishy? And he's like, yeah, it must be magic. I'm like, yeah, whatever, it's magic. So we moved on. And of course, as usual, I'm a damn astrophysicist. I'm gonna figure this out. As we do, but still basic stuff. Nothing out of the ordinary. But you know what? Like I was just there recently, and I took him out, to grab some chicken nuggets as you usually do for an 11-year-old. He's really happy about it. And as we're leaving his favorite establishment, he was like, "Hey, how many particles are there in a human body?" I was like, well, I don't know, we could calculate it. We calculated it, and then he said, how many particles do you think there are in the whole world? And I was like, the world? Come on, get out of here, kid. It's like basic stuff. Like, we're like one planet of many, many, many. And he's like, do you think there's more than 1 trillion particles on Earth? Like, for sure. No question. We calculated it's a lot. And then he blew me away. And then he was like, hey, how many particles are there in the whole universe? I was like, damn, okay, all right, now we're getting somewhere. So, he's 11 now, so he's coming up with more advanced questions that I gotta keep up. And, yeah, so spoiler alert, I wrote my PhD in theoretical cosmology, so, because he asked me that, yeah, and I knew he was gonna ask me and travel back in time and everything. And I was like, I better learn this stuff, so I was like, I got this, not a problem. And besides that too, I know how to Google stuff, so I do it. And actually there's a lot of stuff on this, and once we calculate this from basic cosmological physical principles, and I did it, so we did it. And it was a really weird conclusion at the end, so that's why I wanted to talk about it. So, in order to get at this, how we can figure out how many particles there are in the whole universe, we gotta go back to the very, very basics. And in particular, I want to say that when we talk about particles and atoms in the universe, it's really mostly protons and neutrons right? And so most of the stuff out there is really hydrogen, it's about 75%. And then there's also helium, about 25%. In fact, it's an isotope of helium, which we'll get into. So really, most of the stuff that we really got to focus on is that very top part of the periodic table. So basically hydrogen and helium, these two. And now, in order to understand how much of this stuff exists, we actually have to go even further back. So this is where, luckily, when I was studying this stuff in my PhD program, I was paying attention. So, so here's the history of the universe. And of course, I pulled up the slide when I was explaining this to him. So here we are today, right there. And it's taken quite some time for the universe to evolve to this point. And if we go back, way back, about 14 billion years or so, we find that as we go further and further back, the universe gets smaller and smaller, or things seem to get closer and closer. And the way that we figure that out is by looking at really distant things all around us, just observing, and you see that when something's further away, it's moving basically faster. So you can turn back that arrow of time, and everything is effectively all coming back to a single point. So this is how we figure out that the universe it's expanding rapidly. So as you go back further and further, things get pretty hot, hotter and hotter, and at some points you don't really have hydrogen anymore, you don't really have helium anymore, and eventually stuff cools, and you have around this time here, at about 10 to the minus 5 seconds or so, you have that nucleons form. So things in effect are cold enough where they can stay together bound. Right? So that's this is during the time when we have these nuclei forming. So it looks something like this. You got these positrons, neutrinos, all these crazy particles all over the place. They're all interacting. It's a pretty chaotic mess. And then suddenly these things come together, and finally the universe is cool enough where it's stable enough, and now you've got this pretty awesome helium core. It's 2 hydrogen, 2 proton, and also beyond that too, a bunch of hydrogen. So in order to understand better what these isotopes are, so you've got hydrogen, helium, and there's some main isotopes that go into basically this freeze-out process, or that is, when the universe is that particular age, suddenly these things form and they coalesce, and you have these stable atoms. So this is actually one of the major triumphs of cosmology. It's called Big Bang nucleosynthesis, and it's the theory of where you take basically the very basic laws of nuclear physics, run the universe as we know it, we look back and we observe, and then you effectively find that you can predict pretty well the exact number ratio that you expect from hydrogen and helium 4. And not only those two, but even down to like 10 to the minus 9, 10 to the minus 10 abundance levels. So these are percentages. So this is quite a large order of magnitude range. So it's one of the major triumphs of cosmology. And from there we know that, roughly speaking, if we're doing like an order of magnitude calculation, it's mostly hydrogen and mostly helium, about 75%, 25%. And if you want to get super duper specific, you get to like 10 to the minus 4, 10 to the minus 5, but let's forget that. We're going to get a rough number. So one thing to note is that baryons, or protons and neutrons, are made up of something else. They're also made up of particles. So there's quarks, 2 quarks and a down quark for protons. And at the time when I was explaining this to my nephew, he was like, wait, but are particles made of particles? And I was like, no. Okay, I didn't say that, whatever. Maybe I did. Alright, so after that, also neutrons are also made of 3 quarks. So it's important for us to remember, keep it in the back of our minds when we're thinking about this stuff, is that per proton and neutron, we've got 3 particles basically there. Alright, cool. So main thing to know. 75% hydrogen, 25% helium, and we know what it's made of. Great. So now we need some information from another source, cosmological source, which I'm not going to get into specifics of, but way back when, there was a time where finally photons were able to stream well, and so when you look at all different directions in the universe, we find that these free streaming photons are roughly the same temperature, and also, beyond that too, implies a lot of interesting things about cosmology. But from there we know, we get this pretty awesome map, which I won't get into either, but we know the critical energy density of the universe. That is, we know roughly, well, we know exactly after from these measurements that the universe is basically 8.64 times 10 to the minus 30 grams per centimeter cubed on average. This is like the average density all throughout. Of course, here, there's a bit higher density, right? I mean, there's us, we're around, and also planets, galaxies, things like that have higher densities in general. But all over, on average, that's the overall density. It's a lot lighter than water even, a heck of a lot lighter. And also, the next thing to note is that the density, that is the energy that is in the universe, right? Of it that is made up of baryons only, it's about 4.85%, right? So you can imagine, right? You could take, this is the total energy density per cubic centimeter cubed, and then we multiply by this ratio, by this fraction, and we're going to figure out how much energy density is due to baryons. Okay, next thing to know is that the universe is about 4.38 times 10 to the 28 centimeters. I just kept all the units the same, right? So this was already, I just looked it up and found that centimeters, so I was like, okay, so calculated like 90-something billion light years and centimeters, that's what it turns out to be. After that, the next thing to know, like we mentioned before, was that the majority of the universe, anything that's massive, is basically made up of baryons. That's protons or neutrons. There's also massive particles, there's photons, etc. But let's not worry about that. Let's only worry about like material things. It's the main thing I was thinking when I did the calculation. Anyway, so you need to know that basically a proton and neutron are roughly the same. They're roughly the same mass. I mean, in terms of order of magnitude, for an 11-year-old, he's not going to care. We're just going with the same mass. Cool. So from there, you can imagine if you take the energy density, right, and then you take the fraction of baryons, and then after that you take 4 pi over 3 L cubed, right, the whole volume of the visible universe, observable universe, we're going to basically get the total energy of baryons in the whole universe. Divide that by the mass of proton, and you're going to have the number of baryons. Cool. So you can do that. So like I was mentioning, you take this number, you calculate it, and you get the energy density stored in just baryons. After that, you multiply by this volume factor, and you're going to end up getting the total energy stored in baryons. And after that, divide by the mass of the proton, and we're going to get the number of baryons in the universe. It's a number I didn't bother calculating, and I'm a theorist, so just leave it there. Cool. Wait, what? Are people upset? I'm sorry. I don't care about numbers. Anyway, but I do. Some of them, like you. So, we mentioned before, 75%, 25% helium. And one thing that's interesting to note here is that they're actually, it's by mass, it's not by number. So, basically, you could work it out. I mean, you could look at the atomic number, etc. You could figure out that there's roughly 12 hydrogen atoms per helium atom. Just based on the percentages of from Big Bang nuclear synthesis, from looking back and observing, we know that's roughly the ratio that it should be. Cool. So from there, let's count the particles, right? So if you've got 12 protons, and each one of those has 3 quarks and 12 hydrogen atoms, and also there's going to be 12 electrons in order to make. I'm also assuming that the universe is like is basically neutral, electric neutral, which is not. You know, it's pretty. It's really. I don't think anyone's going to disagree, probably. I hope. And you end up getting 48 particles for the hydrogens, for that component of hydrogen. But then you also need about 1 helium atom for the 12, and then from here too, if you count them up, you're going to have 2 protons, right? You're going to have 3 quarks, and then 2 neutrons are going to have 3 quarks as well, and there's going to be 2 electrons, so you're going to have 14 particles. Cool. So in this ratio, basically, per 16 baryons, there are 62 particles, so we have to multiply our total baryon number by 62 over 16 to convert from baryons to particles. Okay? It's like very basic unit conversion. So I did that. It turns out to be 3.875, exactly. Very nice. So there's this calculation I said before, the mass of proton, then conversion of particles, and we did the calculation, and it turns out there's about 10 to the 80 particles in the universe. 3.4, don't forget that part. We're talking about like order of magnitude calculation. And earlier he also asked me, he was like, hey, so how many particles are in a human body? want to kind of like figure out like what ratio, you can work it out. It's about 1.46 times 10 to the 29 particles. Fun. Okay. But then what's really kind of weird, and this is the sort of weird conclusion after we do this calculation, is that the population of humans on planet Earth is 11% roughly per year. So you can therefore calculate how long it would take for all the particles in the universe to be made up, to make up only humans. Right? And I was like, it's just, you know, like a random Christmas time curiosity, just hanging out in my flip-flops, Ethan, taking a little bit chicken nuggets. And then we calculated this. I expected this to be some crazy number. As a cosmologist, sometimes you do these calculations to check that things make sense. It's great to just do random checks of things you think should make sense, you check that. And sometimes you'd be surprised what you find, like this time. So I expected it to be something like 10 to the 20 times like the age of the universe or something crazy. It ends up, it's 8,600 years. I was like, wait, there must be an error. That's strange. But I double, triple, quadruple checked it, and all you have to assume is that there's going to be an 11% growth every year, and it's going to take 8,600 years to just take up the entire universe. That's crazy. So it turns out my nephew's silly question led to a mathematical proof of a future apocalypse. I wish we weren't happy about that. It's kind of like almost a proof, like for sure things aren't going to work out, guys. I'm sorry. It won't. It just can't. Anyway, something's going to have to happen before then. I don't know what. I think even if like it was like humans on top of humans is growing at this rate, I think eventually we would like break the speed of light and grow. I mean, this is a crazy rate. And actually, this is like a pretty interesting, I think, example. Sometimes, like, you ask some really silly question, or maybe not even silly, but this is how research works in a sense. If many people are in the audience are not like researchers or scientists, sometimes you ask some random question, any question. You could say, hey, how many particles are there in the universe? Turns out, when you do the calculation, you get some crazy different result, like it must be dark matter or something. And in this case, it's like, well, humans will probably not be around after 8,600 years. So that's it. Credits also to a really great review by Numberphile on YouTube for doing a lot of calculations, and I corrected a couple things that were wrong there, but it's all perfectly fine. Right? Thanks.
We will now take questions.
Okay, questions.
Did you factor in infant mortality?
I'm sorry?
Did you factor in infant mortality?
Did I factor in infinite mortality?
Infant.
No. Next one. I did not know. Yes. I think he wants to be a fireman. Yeah, that's what he wants. Yeah, or I think. Okay, let's see. Anyone else? Cool. Okay, thank you, everyone.